Percent yield is an important concept in stoichiometry and chemistry because virtually no reaction runs to completion. No reaction uses up all of the reactant, even if it's the limiting reagent. And that's a consequence of something later you'll learn about called equilibrium. Eventually the reverse reaction kicks in and you end up with a balance of reactants and products, and you don't get a complete production as a consequence. So we like to talk about percent yield, and it's like any other percent, it's a part to whole ratio. But in the case of a percent yield for a reaction, it's really the part is how much stuff you actually get, how much product you actually produce, what we call the actual yield, and the whole is what you should have been able to produce. And since you're only supposed to produce it and don't, it's called the theoretical yield. So you need to know how much of a product you actually get and how much you should have gotten to do it. And as a simplistic example, we'll go back to building cars. If you're building a sports car, you need 2 doors plus 1 engine plus 4 wheels to make 1 car. And let's say that on a given day, you've got 200 doors, and of course with 200 doors, since you need 2 to make each car, you could produce 100 cars. And with 300 engines, given the fact that you need 1 engine per car, you could build 300 cars. And with 600 wheels, and the fact that you need 4 wheels per car, you could build 150 cars. So we know what our limiting reagent is that day. It is our doors. And based on our doors, we theoretically, if we worked all day long, could make 100 cars. Unfortunately, let's say a strike ensues at the factory and only 70 cars are built. Well, what would the yield be for that day? The percent yield. And since we actually managed to produce 70 cars, but theoretically, based on our limiting reagent, we should have produced 100 cars, we have an actual to theoretical ratio of 70 to 100. And like any percent, we then multiply by 100, and we get a 70% yield that day. As a second example, let's consider this problem. If 20 grams of nitrogen are reacted with 20 grams of hydrogen, and 19 grams of ammonia are produced, now because I say they are produced, that is in fact the actual yield. And we want to know what the reaction's yield is. Well, again, I think what is a yield? Well, it's the amount of product you actually get relative to the amount you should have gotten based on your limiting reagent, the theoretical amount. So the first thing I have to do is write a balanced equation for any stoichiometry. Nitrogen, N2, reacts with hydrogen, H2, the product ammonia, NH3. We have to conserve mass and always balance the equation. 2 nitrogens, 2 ammonia molecules. 6 hydrogens require 3 hydrogen molecules, and we're balanced. Now, the theoretical amount I should get depends upon my limiting reagent, because after all, I can only make as much as theoretically using all of what runs out first. So I have to find who's the limiting reagent, and I do that by first converting to moles, both of them, both reactants. And of course, since 1 mole of nitrogen is the equivalent of 28 grams of nitrogen, and 1 mole of hydrogen is the equivalent of 2 grams of hydrogen. Quick conversion gives me 10 moles H2 to start the reaction, and let's see, that would be 0.741 roughly moles of nitrogen to begin the reaction. And of course, I would want to adjust these by their coefficients to get who's actually always going to be limiting, because I might have more of one than the other, but by requiring more, we might actually have a limiting reagent for the more abundant reactant. So when I do this and I get these two values, even when adjusted for the coefficients in the reaction, I see that I have far less nitrogen for the reaction than I do hydrogen. So nitrogen is my limiting reagent. So now I can do the problem very simply. If I have 20 grams of limiting reagent, nitrogen, and 1 mole of nitrogen is 28 grams, because of course I must use moles when I'm doing stoichiometry. Well, given the 1:2 ratio, for every 1 mole of nitrogen, I theoretically could make 2 moles of ammonia. And this is the theoretical yield. It's calculated on using all 20 grams of the limiting reagent in this example. And so theoretically, if ammonia is 1 mole for every 17 grams, it means that theoretically, if I consumed all of my limiting reagent, I could get 24.3 grams of ammonia. So you see, that's theoretically what I can produce. And in the problem, we were told we actually only got 19 grams. And that's to be expected. I am never going to get 100% yield. I'm only going to get a fraction of my theoretical amount. So if I were to take 19 grams, my actual yield, and divide by my theoretical yield, 24.3 grams, as a percentage, we get a 78.2% yield. The molecules went on strike at noon, and instead of producing the 24.3 grams for which our inventory told us we could be able to make, we instead only made a fraction of that and got a 78% yield. Another valuable use of percent yield is as a conversion factor. And you're saying, well, what kind of conversion can I do with an actual to theoretical ratio? And very simply, if you know the, need to get this pen working here, if you know the actual to theoretical ratio, otherwise known as percent yield, you can use it to convert the theoretical amount of what you should have gotten based on your limiting reagent, how much you had, to what you actually will get. Or vice versa. If you know what you actually got, you can use the percent yield to calculate theoretically what you should have gotten. So as a simplistic example, we'll go back to our factory of cars, where we knew that the 200 doors were the limiting reagents, because we could have built 100 cars based on doors, we could have built 300 based on engines, and 150 based on wheels. And in this problem, we're given the yield, namely there is 60% actual production for every 100 you theoretically could produce. And the question is, how many cars were produced? And if we produced them, they're an actual number of cars. So again, very simply, I start with my limiting reagent, as with virtually everything you do in stoichiometry, and that was 200 doors. And how many cars should we get with 200 doors? Well, since we use 2 doors for every 1 car, we should get, and I'm going to label this TY. That's my theoretical yield of cars. It's based on my limiting reagent. It's not necessarily what we're going to get, but we should be able to make theoretically this many cars. And then I use my percent yield as a conversion from theoretical to actual. I can say there will be 60 cars actual yield for every 100 cars theoretical yield. And the theoretical yield of cars is replaced with an actual yield of cars. And yes, that day we should get 60 cars. Not the 100 we were expecting, but the 60 we actually get. So for a more practical example in chemistry rather than the automotive industry, if we had our same reaction, namely we had the 3 moles of ammonia resulting from the production of 1 mole of nitrogen with 3 moles of hydrogen. Excuse me, this would be 2 moles, not 3. If we go back to the last reaction we had, but in this case we have 10 grams of hydrogen and 100 grams of nitrogen, and we know that there is an 80% yield, namely 80 grams actual yield of product for every 100 grams theoretical yield of product. What mass of ammonia is produced? In other words, we don't care how much could you make. We're not interested in the theoretical mass. We want to know what you will actually get. We need an actual yield. Well, as with any limiting reagent situation, first you got to find your limiting reagent. 10 grams of hydrogen, 1 mole of hydrogen is the equivalent of 2 grams H2, meaning initially this reaction presents itself with 5 moles of hydrogen. And then with 100 grams of nitrogen, and 1 mole being the equivalent of 28 grams of nitrogen, it means we begin the reaction process with 3.57 moles of nitrogen. And of course, initially the temptation to say, well, simply because we have less nitrogen than hydrogen, it's the limiting reagent, but that doesn't take into account we need 3 times more hydrogen than nitrogen. So if I divide each by its coefficient, this gives me 1.67, and 3.57 divided by 1 gives me 3.57. This is a smaller value, meaning it's actually the hydrogen in this case that is limiting. And you say, well, all stoichiometry depends on that limiting reagent, because whether you're talking theoretical or a reduced actual yield, how much you can get always depends on your limiting reagent. So I start with my limiting reagent, 10 grams of hydrogen. I need moles to work stoichiometry. 1 mole of hydrogen is the equivalent of 2 grams. And now I do the stoichiometry. For every 3 moles of hydrogen, we should get, theoretically, 3 moles of hydrogen. We get 2 moles of NH3 theoretical yield. And it's important that you label it as such when you're talking about a product, because there are actual amounts of product that you end up with when the reaction's over, and there's this theoretical amount that you could get if you start with that much hydrogen. Why not? Why can't we get that? Well, it's that pesky thing called equilibrium you'll learn about later. But since I'm asked for what is produced, I'm asked for an actual yield. And the percent yield lets me make the conversion, because I get 80 grams of the product actually, AY. For every 100 grams we get theoretical yield. And the theoretical and actual, I'm sorry, I can't cancel a mass with moles. So I did have to make a molar mass conversion first, and for ammonia, 1 mole ammonia is 17 grams ammonia. And then the moles of ammonia would cancel moles of ammonia, and the grams theoretical yield would cancel the mass of theoretical yield. And upon calculating the final answer, we get 45.3 grams of ammonia as our actual yield. Had we not included this conversion from theoretical to actual, we would have had 20% more, because based on 10 grams of hydrogen, we should have been able to make slightly more ammonia. And that's how limiting reagent plays a role in chemistry.